All right, welcome to this live stream. God bless. So I'm Philosopher, my name, and I'm really glad for this opportunity with Joel Academy. So it's a very, very great improvement. So welcome to this live stream. So as seen in the flyer, you know that I'm going to be taking you about chemistry, CHM111, and I'm going to be talking on periodicity, then which I'm going to talk about all this things that you see on the board and show you some periodic properties. But before that, I would like to know your name, your department, where you come from, and like. So you can use the live chat. You can type your name, your department, and all. Okay, welcome. So we can start now. While we do that, then we can start. So as you can see on the board, I've taken periodicity, and periodicity is talking about the periodic tables, and we know that chemistry as a whole depends on the periodic table because we believe that the combination of atoms give us elements, and chemistry is all about the combination of bonds and breakage of bonds, and this cannot be done except we have elements. That means, as a chemistry student, starting your study with periodic table is not out of point. All right. So periodicity will tell you about why some elements combine the way they combine, and tell you a lot of things about chemistry. So if you can be so good in your knowledge of periodic table, it's going to help you to scale very high as a chemistry student. Okay, all right. So now, but if I'm going to take you the periodic table, there are some people that have contributed to this periodic table, and they are great scientists that have done a lot of work. And we have to revert back to history because their work are so unique that they cannot be undermined. Together. So as you can see on the board, I'm going to be talking about these scientists, from Prout to Döbereiner to Cannizzaro to Chancourtois, Döbereiner, and down to the modern periodic law that come through the findings of Moseley. So Prout was the first scientist that first talked about that said something about periodicity. And what was his contribution? He was the first person in 1875 that actually talk about periodicity. It tells us that all elements are as a result of coalescence of hydrogen atom. Don't forget that hydrogen is the first known element, with atomic number of 1. And then since hydrogen is the lightest element, and that was the first element that is existing as of then, so Prout actually now said any other element that we have in the periodic table are as a result of combination of hydrogen atoms. That means the next element that we have, which is lithium, which is helium, that's atomic number of 2. So it's from combination of 2 hydrogen atoms, right? So that will give helium. That's what he said. But we don't notice that these things are not true because there are some elements that does not contain whole number ratio, and then we have discovered a lot of elements like that. So that is why his own theory was actually cut off. Then DJ Döbereiner also contributed his own and talk about it. He said a lot about the periodic table and said that elements in the periodic table, they are actually related. They are actually related by a lot of factors, and then he propounded that we can measure them through their atomic weight, and he propounded the law that we call triads. And what is triads? Triads is talking about, he grouped the elements of the periodic table into various categories, started from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then after neon, we have sodium, then we have magnesium. So what Curtis was saying that if we have elements in group 1s, hydrogen, sodium, lithium, and potassium, the triads is when you are taking them in group of 3. The word tri means 3. So that's triad. So what he said is that for us to get the atomic number of lithium, which is the middle element, it is gotten from the combination of the atomic mass of potassium. Okay, lithium should come before sodium, lithium, then sodium. So for us to get the atomic number of sodium, then if we can add, because we know that potassium is 19 and lithium is 3. So the triads is that the middle person, if we are going to get the atomic number of the middle person, which is sodium, it has to be the summation of the atomic of potassium and the atomic number of lithium, and then all divided by 2. And then if you add this one together, 19 plus 3 will be 22. Then divided by 2, that will be 11. And of course, you know that sodium is having atomic number of 11. But this thing is not true for all elements. It's not true at all because there are some elements that if you group them in threes, like here now, hydrogen, helium. Helium is in group F, is with this noble gas. That means, of course, the next person that is in group 1 is lithium, beryllium. Okay, beryllium is here. So now, if you group them, beryllium, under magnesium, we still have calcium. So that means there are some elements, you can still work this one, you can try it, but there are some, when the periodic table become more wider, there are some that the triad does not work, and that's a limitation to its work, right? Then Cannizzaro, during this period, Cannizzaro actually now talk about what we call valency. Valency. He assigns some numbers. He assigns some numbers to elements. Like now, hydrogen, he said the valency of hydrogen element. And what is combining power? That means if hydrogen is going to involve in bonding with elements like chlorine that is in group 7, that is negatively charged because it's a non-metal, and it's going to bond with 1 degree. And he said that these numbers are called valency and they are the combining power of elements. That is why oxygen that has the valency of 2 need to invite 2 hydrogen so as to make the popularly known structure of water. All right. Now, then we move to the next scientist, A.D. Chancourtois. So him to actually talk about the periodic table, and he actually give us this theory that we know as the law of octaves. All right, there should be a scientist here. That's John Newlands. John Newlands, sorry for that. John Newlands. He was the one that talked about the law of octaves. And if you are familiar with music, you will know that there's something we call octaves in music, and if you remember your notes, do, re, mi, fa, sol, la, ti, do. Then if you count 1, 2, 3, 4, 5, 6, 7, 8, this is octave, octagon, 8. So it means that if you can start from like a particular element, let's say lithium now, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then it said if you start from this, you can 1, 2, 3, 4, 5, 6, 7, 8. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. The next person that you're going to be seeing is sodium. So he's actually saying that, let's say your lithium start from here and you start counting from here, lithium, beryllium, boron. It's saying that for you to go back again from where you start from, this element will fall under here. So if you are sharing the element from lithium, do, re, mi, fa, sol, la, ti, do to the 8th figure, if you are going to start again, the sodium is going to be here. That means every first element in an octave will look like the 8th element, right? That means the reason why sodium and lithium are in the same group is because when you count after lithium, if you count 8, 1, 2, 3, 4, 5, 6, 7, 8, it's going to be octave. But if you don't know that during this time, the noble gas, neon, are not included in the periodic table. It was later on that we have the neon. So we can actually terminate this neon and bring sodium here. So as to actually affirm what we are talking about. Now, that means if do is lithium, by the time you say do, re, mi, fa, sol, la, ti, do to the 8th note, it's going to be another person in that group, which is sodium. And you will see that lithium and sodium are in group 1. And that means so it was the one that gave us this law. And what is the law of octaves? It states that every first element will look like the 8th element, counting from the elements, and that's the law of octaves. But this law has a lot of controversy, and it creates a lot of controversy in science, and it was actually rejected for 2 reasons. And then, please, I hope we are following. Like, please, if you are following, you can type in the live chat and say, so you can type in the live chat and say, I'm following. So if you are following, you can show that you are following. All right. Thank you. So you can send your favorite emoji or mention your name or something and say, I'm following. All right. Thank you. All right. So I'm still on John Newlands. I said John Newlands' law of octave was rejected because of 2 reasons, which you have to know. The reason why we are revisiting these histories is just for you to help you in your theoretical knowledge about periodicity. Now, the first reason why John Newlands' law was rejected was number one. In science, we do not allow you correlating science with spiritual laws, with mystical stuffs. Because to John Newland, he believed that there is a mystical relationship that exists between music and chemistry. Mystical relationship that exists between music and chemistry. Maybe because between music and chemistry. You want to write it down? So the first reason why his law was rejected was because he believed that there's a mystical relationship between music and chemistry. And scientists does not believe in some spiritual laws. Like there's no might in science. We believe on experiments. When you observe something, you perform experiments, then you provided a theory. So because of this belief, him trying to connect music to chemistry makes so many scientists to disprove his work. And another thing is that his law of octaves does not work for elements beyond calcium. Calcium is element 20. So that means from scandium downward, the triads, the law of octaves, like saying that every first element loaded at the eighth one does not really hold. And that's why it doesn't hold well. It does not hold well for all, elements. So that's the law. Please, I want to correct this. This is not 7, it's 1815. 1815, I remember now. It's 1815. So Prout, 1875, of course, is too close, so it's 1815. Döbereiner was the first person that discovered that there's even elements. The elements are from the coalescence of hydrogen. He was the person that talked about elements, and then all these guys continue his work, right? Then, so we have learned about, let me make a quick review. I started with Prout. I said Prout is the first scientist to talk about elements. The elements are the coming together of hydrogen atoms, the first known element. Then we moved to Döbereiner, which talk about the atomic weight of elements and tell us a lot of features about elements. Then Cannizzaro, they now discover the valency, which is the combined power of elements. Then followed by Newlands, that give us the law of octaves, that shows some trends about some discovered elements, that if you can actually check the first element and the eighth one, you are going to see that there is a correlation between them. And the next one that we are going to check to now is the Chancourtois. And what is the contribution of the Chancourtois? So the Chancourtois actually now continue the work of John Newlands, and also support him with his law and continue. He uses a circle triangle, which is of 16 units, and then to describe a lot about the atom. And he said that there's a regular trend between atoms. There's a regular trend between atoms, and he said the volume of elements is their mass all over density. Of course, you know that density equals to mass over volume. So D equals to M over V. So if you invert the formula, volume will multiply density, and then mass will be equals to density times volume. So if you have to make volume the subject, you divide both sides by density. So he said the volume of every element is a mass over density. Like now, these two scientists that we are moving to now, Döbereiner and Mendeleev, they contributed a lot to the development of our modern periodic table. The periodic table that you have with you now. The periodic table that we have. Hello? Are we still together? All right. So Döbereiner and Mendeleev, they are giving more regard because they contributed some great work into the periodicity that we are talking about. So Döbereiner actually talked about, he was the first person to arrange elements in order in the periodic table in vertical and horizontal row. You notice that elements that look similar can be arranged in a row, and he called that row the period. So he arranged elements in periods, and then move and shows that some elements have similar properties, and because they have that similar properties, they have to be in the same period. Then Mendeleev, if you are familiar with your secondary school textbook, you see that we have been hearing about Mendeleev. Is part of the periodic table. Now, why we are not talking about all this scientists is because Mendeleev was actually the person that contributed majorly to what we have today. So, according to history, Mendeleev was the first scientist that divided the periodic table into groups and periods. Though Mendeleev is still using atomic weight, there is a kind of uniqueness in Mendeleev's work because Mendeleev actually was precise and was certain. He made a lot of research about his findings, and he give in details all the analysis of each of the elements that he said. There are about five uniqueness to Mendeleev's work. Number one, he keep to its theory that said elements that have similar properties must be in the same group. So he did not even bother about the atomic mass of some elements. Maybe the first one in front is more than the next one. He just makes sure that every element that behaves similar are in the same group, regardless of their atomic mass. But at this point, even with Mendeleev, we are still using atomic mass to categorize elements in the periodic table. And he was the one that first gave us the group and the periods. Then he makes the groups the column, and he makes the period the rows. And by then there are some limitations to his findings, and which I would like us to note. Number one, he uses atomic mass instead of mass number, instead of atomic number. Atomic mass instead of atomic number. Then another fault to his theory is that he actually placed some elements with higher atomic mass before the lower ones, like in the place of cobalt and nickel, in the place of potassium and argon, then in the place of tellurium and iodine. Now, if you check these two elements in the Mendeleev periodic table, it's actually cobalt. Nickel comes after cobalt, but he places the atomic mass of nickel is more than cobalt, but he brought nickel before cobalt, and same thing for argon before potassium, then same thing for tellurium before iodine. So all this ambiguousness is what led to the limitation we have observed in his theories. Then also, elements are not grouped according to their numbers, like the number are not sequenced. We see some elements that are more higher and behave very different from what he groups. But even at that, we must commend the work of Mendeleev, because Mendeleev was so specific that he even predicted some undiscovered elements. He predicted some undiscovered elements, and all he said about those elements after they have been discovered actually later came true. An element that formed into that category is scandium, and gallium, and germanium. This element, germanium, is 3 out of 10 that Mendeleev predicted their properties even before they are discovered. And when we later discovered them, we noticed that it is very, very true. That its figure is very true. And this one is known as Eckhart boron. This one is known as Eckhart boron. That was the